Okay, Year 10, we're up to our fourth lesson for this topic, which is nonlinear relationships. And in this lesson, we're going to look at higher powers of x. So far we've learnt about reciprocal functions and how to graph hyperbolas. We've learned about exponential functions. And then last lesson, we looked at circles and semicircles. Let's start with cubics. The equation y equals x cubed is a cubic relationship. We can tell that because the highest power of x is a 3. Now when we graph this, it's going to be a little bit like a straight line in that it will start in the third quadrant and end in the first quadrant. But unlike a straight line, it's going to be a curve. It's going to come up through here and then turn through 0, 0. Sometimes we call this a dog leg. Now higher even powers follow the same patterns as parabolas. So y equals x to the power of 4 will look like y equals x squared, except it's going to be wider where it turns and then steeper up here at the ends. Higher odd powers follow the same patterns as cubics. So y equals x to the power of 5 looks like y equals x cubed, except it's wider where it turns and steeper on the ends. If we want to graph cubics, we can plot points. So suppose we want to graph y equals x cubed plus 1. We could draw up a table of values, plot the points. Remember that it's going to be a curve and try and join the dots. Don't join them with straight lines. Draw a curve through it. Nice smooth curve like that. Now the general cubic equation has more than just the x cubed term. It looks like this: y equals ax cubed plus bx squared plus cx plus d. And the graph, instead of coming up and doing that funny turn through 0, 0, it's going to look more like this. It'll come up, turn around, go back down, turn around, and then go up. Now, it will have exactly one y-intercept, and you can see that on this curve. It has an intercept at 0, 6. But it could have 1, 2, or 3 x-intercepts. So this one here's got 3. It's 1, 2, and 3. If we shift this curve up slightly like this, so that it just touches here, then it's going to have 2 x-intercepts. And if we shift it up a bit further, then it's only got the 1 x-intercept. All right, let's have a look at how we might graph one of these cubics without using a table of values. We're going to use the features of the curve. Firstly, we're going to find the y-intercept. It occurs when x is equal to 0, so we're going to put 0 in where the x's are. And pretty obviously, y is going to equal 0. So the graph's going to go through the origin. Next, we're going to find the x-intercepts. They occur when y is equal to 0, so put 0 in here. And we're going to use the null factor law, but we've got 3 products in this case: x, x minus 1, and x plus 2. And any one of them could be 0, and that would wipe the whole thing out. So our x-intercepts are 0, 1, and negative 2. These, by the way, are also called zeros or roots of the equation. All right, let's plot those points. So we've got, it's going to go through the origin, it goes through 1, 0, and it goes through negative 2, 0. The final piece of the puzzle that we need is, does it start down here and end up here? Or does it start up here and go down here? And that's to do with the coefficient of x cubed. Now if we just pretend to expand this out in our heads, we're going to get positive x cubed. So this is a positive cubic, which means its tail is going to be in the positive quadrant up here. So it's going to start down here and end up here. So let's have a go at drawing this. It doesn't have to be super accurate. I've just got to get through all of those points. So coming up through here through 2, curving around through 0, up and around through 1, I missed it a little bit, and arrows on the end. And there's our graph. Okay, let's have a go at graphing a quartic curve. That's an x to the power of 4. So remember, powers of 4, the graphs are going to look like parabolas. If it's a positive curve, it's going to start up here and end up here. If it's negative, it'll start down here and end down here. So that's going to be the first place I'm going to start. Is it a positive or negative curve? We need the coefficient of x to the power of 4. So let's pretend we're expanding this out. X times x times x times x is 1x to the power of 4. It's positive. So that's good. It's going to start here and end up here. Next, we're going to find the y-intercept. Y-intercept occurs when x is 0. Putting x equals 0 here, it's going to wipe the whole thing out. So the y-intercept is 0, 0. Now finding the x-intercepts, put the 0 in here. That's going to give us 0, 1, negative 2, negative 1. All right, we're ready to go. Let's just plot those points first. So it's going to go through here. It's going to go through here. It's going to go through negative 2, and it's going to go through negative 1. And we're starting up here and ending up here. All right, it's going to look a bit dodgy, but never mind. Here we go. Comes down through here and then up and then turns around. It's going to look like a W. Oh, always missed the last one. And put some arrows on the end. So roughly, that's what it looks like. All right, let's finish off with a negative graph. So this is a cubic. We can see the highest power is 3. But the coefficient of x cubed is negative. So normally a cubic goes this way. Instead, it's going to flip over the x-axis. It's going to start up here and end up down here. So let's put that in. Starts here, ends down here. All right, y-intercept occurs when x equals 0. This one's not nice. I need to put 0 in there, and in there. Let's write it out. This is negative 1 times negative 1 times 2 times negative 2. Multiplying that all together, we get negative 4. So it's going to cut through here. Now we want the x-intercepts. So we're going to put 0 in here. Now we can see that they are going to be 1, negative 2, and 2. So let's plot those points. 1, negative 2, and 2. All right, I'm just going to trace through this and see if we can make sense of it. I want to start here and come down here. And then I need to come down here through that y-intercept and then turn around and come back up here through 1, turn around and come down through 2. Now this is symmetrical through here, so it's actually going to turn before it gets to that y-axis. All right, let's see if I can draw this. It's tricky. It comes down. It's turning. Comes up through 1. Oh, beautiful. And then put your arrows on the end. And there it is. Now, be careful. This equation could also be written that way. So instead of doing negative and then x minus 1, they could put the negative in the bracket and write 1 minus x. But you can still see that that is a negative cubic. Okay, it hasn't changed anything. This is still its graph. So just because the negative is not out the front doesn't mean that it's not a negative graph. Okay, final note. When teachers mark a sketch of a graph, this is what we look for. Did you get the y-intercept correct? Are the x-intercepts correct? Is the shape of the graph correct? Is it a positive or negative graph? Have you used a correct scale on the axes? Remember, the x-axis scale doesn't have to match the y-axis scale. And have you used the correct notation, or have you labelled your axes and drawn arrows on the end of the graph? It doesn't have to be super accurate beyond that. So where it turns doesn't have to be accurate, just those things. That's what we're looking for. Now that brings us to the end of the lesson. This was a pretty big lesson, so you're going to need some practice on this. I would encourage you to sketch some graphs, use Desmos to check your answers, and if you don't know where to start, start by using Desmos because it's a really, really good teaching tool. In our last lesson for this topic, we are going to look at points of intersection.